Well, we've made it through all of the topics that are in a typical Calculus 1 course. This video is going to be a review, kind of the highlights of Calculus 1, and it will really very briefly talk about everything from limits up through integration and area. Let's start off with limits. Now, limits in a typical class is the first thing that you go over. And so since it was the first thing you went over, it's the farthest thing from your current date in the class. So I'll spend a lot of time on the limits, and then we'll kind of go faster as we go through because, right now you're doing integration, which is the reverse of derivatives. So you should be fairly comfortable with derivatives, and you use them through graphing, and you've used them, like when you're trying to find the u substitution for integration, you've had to find du. So that you've still been using limits, maybe not so much. So let's start off with limits. And if you did happen to stumble across this video looking for kind of a highlight reel of Calculus 1 topics, there is a playlist. I'll put the playlist link in the description just in case you need it. Um, but there is a playlist, but in limits, in the playlist, there are 12 videos that take over 7 hours of material. So I'm just going to go through some of the types really quickly. I'm not going to go through all the types. I'm not going to go through the greatest integer, floor function, different things like that. But if you want more exposure and more details about limits, there are 12 videos that consist of limits and then support videos on like factoring and simplifying complex fractions and things like that in there. So they're at this top of the playlist. All right. Now, so let's start off with limits. Now, what is a limit? A limit is where, they I'll write it down in just a minute. But when they write down the limit, they're actually asking you to talk about what y is doing in the vicinity of an x value that they give you. So that as your x gets closer and closer to, let's say, 3, they're wanting to know what y is getting closer and closer to. Please remember that it doesn't actually have to arrive at that y value. It just has to approach that y value. All right. Likewise, it just has to approach that x value. It doesn't have to get to that x value. So we're just talking about behavior, not actual results, okay, like plugging numbers into a function. So if we had the limit as x goes to 2 of x plus 2 over x cubed plus 8. Now, what works for a lot of my students, and actually I use it quite a bit myself, is to make a list. So you have a list of all the different things, so you have a piece of paper and it might break down like, here's my limits section. And in it you go, you're telling yourself, if they say limit, I'm going to look at it and go, can I do this? 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 Some people's lists have a little example right next to what their technique is that they're trying to remember for the final. So you study the the list, really making sure that it's all internalized, that you're ready to recall it. So one of the first things on your list should be, well, what if the x value that they're talking about is actually in my function's domain? If it's in my function's domain, then that means that the function, whatever it is you're going to draw, actually goes through a point where it has an x value of something and a y value of something. So we can just sub it in. So we would go, okay, 2 is in this domain because the restriction on a fractional kind of function is, are you going to get 0 on the bottom? So I'm not, so I'm just going to substitute it in. So this would be 4 over 16, which is a fourth. And even on the final, I like my students to write a complete sentence. Don't know about your teacher. All right. So the first thing if you're making a list would be, all right, if it says limits, the first thing I'm going to try to do is determine if the x value is in the function's domain. If it is, I just sub it in, tell it what the result is. If not, then I start looking for alternative possibilities. All right. So what if it had said, what's the limit as x approaches -2 of x plus 2 over x cubed plus 8? And you're always hopeful, right? We should always begin with hope. So can I use the -2? Is it in this function's domain? No, because -2 cubed is -8 plus 8 would give me 0 in the denominator, so I can't do that. Then you have a list of possibilities. I rank my possibilities based on what I'm happiest seeing. And so, the last thing on my list would be the one I don't want to see. All right. So I'm pretty good at factoring. So I would say, all right, I'm gonna try to factor this. I'm not sure. I'm fairly certain that it might help because I've practiced, but I'm not 100% sure, let's say. All right. So x cubed plus 8 is the sum of two cubes. This is actually x cubed plus 2 cubed. And if you've forgotten how to factor the sum and difference of two cubes, there is a factoring view in the limits section on how to do that. So you write it down without the cubes. You may have heard your teacher talk about something called SOAP, S-O-A-P, same, opposite, always positive. Anyway, you take the term in the front, square it, and put it in the front. You take the term in the back, square it, and put it in the back. Front times the back goes in the middle. If this is a plus, this is the opposite, and this is always a plus. And now you go, oh, hey, this problem, which is this x plus 2 right here, is divided out of the numerator. All right, now some people say canceled. I had some teachers who used to work for me that if you said cancel, they almost became ill. So I usually try to remember to say reduce. All right, but in case I forget, canceling and reducing works for me. All right. So now my problem, okay, the thing that was giving me the 0 in the denominator, which was this factor right here, because -2 plus 2 is 0, that's where the 0 came from. So now it's gone. So now I can substitute in the -2. So 1 over, or at least I can try. I've seen it where it turns out to where it's still 0. And then you have to move on to the next possibility. So this is 1 over 4 plus 4 plus 4. This is 1/12. Now there isn't actually a point of -2 1/12 on the graph. This is a discontinuity, but we use the technique where we can call it a removable discontinuity because I removed this x plus 2 factor that was causing the discontinuity. So the functions behave like each other, but if you graphed it on your calculator and then you looked at the little where you can look at the table, it would give you an error for this one. It would give you an error for x is equal to -2. For this one, it would give you 1/12. All right. I probably shouldn't tell you things like that. All right. In case your teacher doesn't want you to use the calculator. So first thing we do, can I sub it in if it's in the domain? Second thing is maybe I can factor it. Keep in mind that you have to keep writing the word limit until you actually substitute in that -2 because if you have a teacher that wants you to learn how to express yourself in a professional manner, like I expect my students to do, they take off points if you don't write that limit. And it would be a shame to do the problem algebraically correctly and yet have points taken off because of a notation error. So be careful. All right. Now, there was a couple of other types we're going to talk about again. If you want more exposure to this, more um, hints and a couple of more types, go back and look at the playlist at the limits section. Like I said, there's 7 hours worth of limits, and we're going to do these very quickly. So again, somebody asks you the limit about this function. They're curious about x as it approaches 2. You go, oh, can I substitute 2 in? No, that would give me 0 in the denominator. Now it actually gives you 0 in the numerator as well. And that's one of the indeterminate types, which I'm going to talk about in just a little bit. Okay, but if it's 0 in the denominator and you can use some sort of technique to remove the discontinuity, we're going to practice that right now, not the indeterminate form right now. Okay, so you look at this and say, okay, this has square roots in it, and it does look like the square root of x minus the square root of 2 is sort of related to x minus 2, which it is. So you multiply this by its conjugate, and let's see what happens. All right, so the numerator is the FOIL method. So the square root of x times the square root of x is the square root of x squared, which is x. The square root of x times plus square root of 2 is square root of 2x, and minus square root of 2 times the square root of x is minus square root of 2x, and those cancel out. Maybe I better write those down. Okay, so you'd have plus the square root of 2x minus the square root of 2x minus square root of 2 times the square root of 2 is the square root of 2 squared, which is 2, all over. Now, it doesn't look like the difference of 2 squares. You know, when you multiply conjugates together, it's the difference of 2 squares. But remember, I had been saying the square root of x squared, square root of 2 squared, and there's the difference of 2 squares. Just in case you're wondering, how come that isn't like that? Over. Now, this x minus 2 that's in the denominator, it actually is the problem or the restriction that's causing you to not be able to substitute in x is approaching 2. So we want it to go away. So don't multiply out this denominator because we want this x minus 2 to hopefully cancel or reduce out. And if you look at the numerator after you have negated those square root of 2x factors, you have x minus 2 over x minus 2 square root of x plus square root of 2. And since I didn't multiply it out and kind of muddy the waters, it's clear to see that these reduce or cancel out. And you'd have 1 over the square root of x plus the square root of 2. You have to keep saying that limit bit until you actually substitute in that 2. All right, because there's your algebraic manipulations and then there's proper form. And now that you're in calculus class, your teacher should expect proper form from you. You know, maybe before your teachers were like, you know, we don't really care as long as you got the answer. But y'all are now going into professions that need you to take calculus. You have to learn professional format. Notice I'm not saying anything about your writing because mine on these little whiteboards on the computer is a little bit left to be desired. It's better on an actual whiteboard on the wall. All right. Now, for some teachers, 1 over 2 square root of 2 would be fine because now that you're in calculus, they go, well, we know you know how to rationalize the denominator. We're not so concerned about that right now. But in the interest of proper form and this might be not completely finished if you rationalize the denominator. You'd have 2 times the square root of 4, which is 2, so this would be 4. This is definitely proper form. So 1 over 2 square root of 2 may or may not satisfy your teacher, and it may or may not satisfy the computer. I kind of think it wouldn't satisfy the computer. But going the extra mile is definitely not going to hurt you, even if your teacher allows it. Better safe than sorry. Alrighty. Let's look at another one. So then there's complex fractions. So if you have the limit as x goes to 5, Again, you would look at it and say, can I just substitute the 5 in? No, because it gives me 0 in the denominator. And since this is and actually gives you 0 in the numerator as well, which again is one of those indeterminate forms. But to be honest, when you do the indeterminate forms, trying to take the derivative of the top maybe might be more difficult than just cleaning this up. So if you have complex fractions, there's a slower way to do it, which believe it or not, most of the students I've seen cannot do it accurately. And then there's a faster way to do it, and usually the students are better at that. Okay. And so rather than combining the numerators and trying to make them have a common denominator and then working with them in the other denominator, it's easier and to your advantage if you will just clean it up. And so if you look at it, you have 1 over x minus 1 over 5. And in the bottom, you actually have x over 1 minus 5 over 1. So there's 4 fractions within a fraction. And the least common denominator of these 4 pieces is 5x. So if you will multiply the top and the bottom of this by the least common denominator of all the pieces, even within the larger fraction, and you're going to actually multiply across this top and use the distributive property. But when students do that, they often lose pieces along the way. So I say on the top, just write it down next to each term. Keep in mind that on the bottom, we don't actually want to multiply out this x minus 5 because we're trying to make it go away. Because the x minus 5 is what's causing the discontinuity, and we want to remove it. Okay, so we'd have the limit as x goes to 5, and this x cancels this one, and you would have 5 minus, and this 5 cancels this one, and you'd have x over x minus 5 times 5x. Now, this is really close. So I'm going to factor out, I'm not multiplying by a negative, because if I multiplied by a negative, I'd have to multiply the bottom by a negative. So I'm going to factor out a negative. So positive 5 divided by a negative coming out in the front is a negative 5. A negative x divided out a negative is a positive x. So I have the limit as x goes to 5 of the negative, and I'm going to switch these two around so the x is in front so you can see this a little bit better. And these cancel or reduce. And you have negative 1 over 5 times 5. So it turns out to be negative 1/25. So the limit as x approaches 5 of 1 over x minus 1 over 5, x minus 5, is negative 1/25. One, two, three. Okay, now we're going to go on to a little bit of a different one. So if you have the limit as x approaches negative 2 of x plus 2 over x plus 2, where the numerator is in the absolute value, this is not something over itself cancels, okay? Because the absolute value bar should make you kind of suspicious about, All right, now remember that way back yonder in algebra class, they said the absolute value of some number is x if x is greater than or equal to 0. It's the opposite of x if x is less than 0, because the absolute value of a positive is itself, the absolute value of a negative is a positive, or the opposite of what it started out with, right? But I'm going to show you this slightly different way, but you'll see how that's going to come into play. So you'd go, can I substitute the -2 in? No. All right. So you can, this is the way I do it, right? So I'm going to introduce this concept of what I call sneaking up on the number, right? Now there's ways to say you're going to get increasingly close to this value. They'll talk about numerical calculations, but none of that makes me smile. Okay, so if I can say something to make me smile or make my students smile, then that helps your brain to kind of relax a second. So we're going to sneak up on this -2 just to see what happens. So I have a -2. Think of it in the number line. And what you're going to have to do is, up till now, these have all been two-sided limits. Because remember, there's not a plus or minus in the corner, it's two-sided. And if you can substitute it in or remove the discontinuity and substitute it in, the two-sided limit is answered when you get that algebraic solution, right? But if you can't remove the discontinuity somehow, you have to get just really close numerically, right? So like on the left, you might have something like -2.001. On the right, it might be something like -1.999. And so you can't be sneaking up on the left on it and have it be like -2.5. That's too far away. So let's break this down and have the limit as x approaches -2 from the left of x plus 2 over x plus 2. If you can't get it to reduce down, then you have to do the two sides separately. See what happens. So here we go. Let's try a number just to the left. Let's try -2.001 plus 2. And if that x is -2.001, it's the same one here. So this turns out to be the absolute value of -0.001 over -0.001. And the absolute value of -0.001 is 0.001 over -0.001. So it is a version of 1, but this one happens to be a -1. Okay. And the limit as x approaches to -2 from the right of x plus 2 over x plus 2, where the top is the absolute value, would be something like -1.999 plus 2 over -1.999 plus 2. So this is a absolute value of 0.001 over 0.001. So that's 0.001 over 0.001 after you take the absolute value. So this is 1. So if you're asked for the one-sided limit, then it's either going to be 1 or -1. This is the right side. This is the left side. But if the original question that says, what's the limit as x approaches -2 from both sides, because without a plus or minus, it's saying both sides. Since the limit from both sides does not match, then it does not exist. I have students who as soon as they see that, well, I don't know that I've had students do that a lot. I've had students like on their homework, they'll try to say, oh, as soon as they get 0 in the denominator, they say it does not exist. But after I grade it for a while, they don't do that on the test. But you just never know. All right. Let's then try one more, the limit as x approaches 3 of 1 over x minus 3. This one, there's nothing to reduce, nothing to multiply by, nothing to clean up. So this one is just there. Okay. So since it's a two-sided limit, we need to look at both sides. So the limit as x approaches 3 from the left. So if you think of 3, and to the left of it is 2.99, and to the right is 3.001 or something like that. Okay. So from the left, you'd have 1 over 2.999 minus 3. And actually, I don't really care what that number is. I just care whether it's positive or negative because this is a tiny negative number. And any number, even 1, divided by a tiny negative number that's getting tinier and tinier and tinier as you get closer and closer to 3, because you're going to go 2.9999, 2.999999. It's just going to get tinier and tinier and tinier. It blows up bigger and bigger and bigger, so this is negative infinity. The limit as x approaches 3 from the right is 1 over 3.0001 minus 3. I didn't have a little complete sentence there. Okay, so this is 1 over a tiny positive number that just keeps getting tinier and tinier and tinier. So 1 over a tiny positive number is a huge positive number. So if they asked you one of the one-sided limits, it depends on which side you're coming in from. And then, but if they asked you for the two-sided limit, since the two sides don't match, it does not exist. But don't slap that answer down as soon as you see this. Because if you have a sneaky teacher like me, and I don't actually think this is sneaky. All right. What if we squared that? Okay, so then remember what we do is we looked at it from both sides. The limit as x approaches 3 from the left, let's say, of 1 over x minus 3 squared would be 1 over 2.999 minus 3 squared. So you'd have 1 over a tiny negative number squared, which makes it a wee little tiny negative positive, right? Because when you square it, it's going to be positive. So this is positive infinity. And as you approach it from the right, you just have to find ways to kind of, even if it's like rolling your eyes humor, okay, it does alleviate a little bit of the stress of your brain and it functions a little bit better. So you've got 1 over a tiny positive squared, which makes it 1 over a wee little tiny positive number. It's even smaller squared. So this is positive infinity. Yes, I actually say that in class. They all laugh, roll their eyes, as they should. Okay, so the two-sided limit, wait a minute, I can't have them both coming in from the left and the right. Okay, no, this is the right. I got busy with my story and wasn't paying attention to what I was doing. All right, so the limit from both sides, if I could write halfway decent, is positive infinity. So if you had written does not exist, you'd be wrong. So, all right. Now, let's do what happens if you're approaching infinity. And they typically, sometimes they ask you on unusual things, and um, sometimes it's kind of a trick question. For instance, what if they say, what's the limit as x approaches infinity of sine of x? And so you think, well, it's just wandering off down here like this, right? But since the concept is what is it approaching and kind of heading in either that direction, like to infinity, or settling down around a number, sine and cosine and just keep bouncing along, right? They're not settling into a specific direction or anything else like that. So this would be does not exist. But this one, right, if you have something which is the more common type that looks like a rational function, the idea here is you divide each term within the fraction by the biggest powered variable in the denominator. Okay, so the biggest powered variable in the denominator is x. So you would have 3x squared plus 2x plus 5x plus 2, and you're going to divide everybody by this x. That's just a technique you use. Go see the video. All right. So, because there's a whole video on this. All right. So x over x is 1, and we have 2 over x. 3x squared over x is 3x, plus 2x over x is 2, plus 5 over x. Now, as x goes off to infinity and you have 5 divided by this humongous number like a billion or 10 billion or a trillion, then this is going to go to 0. And 2 divided by that is going to go to 0. So those are going to go off to 0. So then you have 3 times infinity plus 2 over 1. Now, 3 times, okay, 2 added to 3 times a billion is really not significant, okay? So you've got 3 times a billion, and you don't write 3 times a billion or 3 billion or 3 trillion. 3 times some humongous big number is just an even larger, more humongous big number. So you still just write infinity. Now, some of you may not have had the e functions and you've had trig. I think most people have e functions in their Calc 1 course. They talk about early transcendentals versus not, but again, you can skip any of this that's not in your particular course. Let's talk about the indeterminate form. So if you have the limit as x approaches 3 of x minus 3 over x squared minus 9. We would, the way we were previously doing it, we would go, oh, can I put 3 in and just substitute it in if it's in the domain? Well, 3 squared minus 9, looking at the denominator, is 0. And we would go, oh, but look, this factors, right? This is the limit as x approaches 3 of x minus 3 over x minus 3, x plus 3. My problem that's giving me 0 and the denominator goes away. So you'd have the limit as x approaches 3 of 1 over x plus 3. So this turns out to be 1/6, right? Okay, but let's use this now that we know the answer is 1/6. Let me show you what happens with what's considered indeterminate cases. So the indeterminate cases say that if you're trying to take the limit and you get something of the form 0 over 0 or infinity over infinity, or you can have 0 minus infinity, something like, or infinity minus infinity, you try to get it into fractional form. And then there was something called L'Hopital's rule, which required you to know how to do a derivative. So they generally have um, all the limits at the front, then they teach you derivatives, and then they come back with L'Hopital's rule at the end of derivatives. And so if you're looking for L'Hopital's rule so that you can get more help with that, then what you would do is go look at the playlist at the end of the derivatives section, and there's like, I think it's 45 minutes or something on L'Hopital's rule that you could go see. So L'Hopital's rule says, if you're getting one of those indeterminate cases where it's like 0 over 0, infinity over infinity, and if the derivatives of the top of the numerator and the derivative of the denominator exist, then you can apply L'Hopital's rule, which says take the derivative of the numerator and then find the derivative of the denominator. Do not get this mixed up with the quotient rule. We are not doing the quotient rule. So we do the numerator by itself, the denominator by itself, and then we can look. Okay, so I always designate L'Hopital's rule by putting a little h right there so that, and I ask my students to do that so I can tell what they were thinking, just in case they accidentally do something like the quotient rule or can't do the derivative correctly. At least I know what they were trying to do. All right, so I had 0 over 0. So I take the derivative of the numerator. Well, the derivative of x minus 3 is 1 over. And the derivative of the denominator separately. Okay, the derivative of x squared minus 9 is 2x. Correct? So then now I can substitute it in. I have 1 over 2 times 3. This is 1/6. So see, unless they ask you to use L'Hopital's rule, you could get it either way, and they're both legal. All right. But sometimes L'Hopital's rule is the only thing that actually works. So what if you have the limit as x approaches 0 of e to the x minus 1 over cosine x minus 1? And you would say, well, let's see, can I cosine x minus 1? Cosine of 0 is 1. So I'd have 1 minus 1. Oh, that's 0 in the denominator. But let's check the top. Maybe I can do L'Hopital's rule because it doesn't look like these factor. They don't have square roots. They're not a complex fraction. I'm kind of at a loss. Let's see if it works for L'Hopital. E to the 0 is anything to the 0 power is 1 minus 0 minus 1. So I have 0 over 0. So this is that indeterminate case. So I am going to apply L'Hopital's rule. And the derivative of e to the x is e to the x. The derivative of minus x is minus 1. The derivative of minus 1 is 0. So you take the derivative of the numerator separate from the derivative of the denominator. And the derivative of the denominator is minus sine x. Now, when you get to derivatives, don't do L'Hopital's rule instead of the quotient rule, where it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So don't mix those two up. All right. So then we try to say, okay, can I just substitute it in now? Nope, because minus sine of 0 is 0. E to the 0 is 1 minus 1. So I still have 0 over 0. So you can apply L'Hopital's rule as long as the derivative still exists and as long as you have that indeterminate case. As soon as like the denominator goes to something other than 0 or the numerator goes to something other than 0, then you can't use L'Hopital's rule. All right, so we're going to do it again. The derivative of e to the x minus 1 is e to the x. The derivative of minus sine is minus cosine. because the minus is just dragging along. So now let's try that. So we'd have e to the 0 over minus cosine of 0. So e to the 0 is 1. Minus cosine of 0 is 1. So the whole answer is minus 1. So the limit as x goes to 0 of e to the x minus 1 over cosine x minus 1. Now, this works also, if you have infinity over infinity. So the limit as x goes to infinity of x squared over x ln x, you would have infinity squared over infinity, because even though the natural log of x is not huge, okay, x is increasing. So it's like, well, what have we ended up with? So let's see what we can do here. First off, I can actually reduce this x and this x squared and have the limit as x goes to infinity of x over the natural log of x, which is still infinity over eventually a very slow infinity. Okay, so we can apply L'Hopital's rule and have the limit as x goes to infinity of the derivative of the natural log. I'm sorry, the derivative of x is 1. The derivative of the natural log of x is 1 over x. And 1 divided by 1 over x is 1 times x. So now I'm not applying L'Hopital's rule. This is the limit as x goes to infinity of x. So this is infinity. And it might have been a good guess just looking at it going, okay, you've got x squared, you've got x and a multiplier down here. I'm thinking it's going to kind of reduce to x. So, but you should still check that out. When you get to the ones like trig functions and e functions and different things, it's helpful to remember what the graph looks like, to think about transformations, like if it's if it was something like e to the x plus 1, where it's lifted up 1 and the horizontal asymptote would go with that. Sometimes a picture is worth it, and some of your teachers will let you do a picture. So for instance, if you have the limit as x goes to pi over 2 of secant x, let's say from the left. Okay, so secant x is related to cosine. So cosine looks like this. And secant looks like this. Everywhere cosine goes through the x-axis, that's 0, and 1 over that is undefined. So it goes like this. All right, so this is pi over 2. So what's the limit for secant as x approaches pi over 2 from the left? So you're coming in this way. This would run off to positive infinity, right? From the right, it's going to negative infinity. I asked this question one time, and it just killed me because I don't think the students actually read it. And I said, what's the limit as x approaches pi of secant x? And I was getting all these infinities and whatnots because they were thinking, oh yeah, secant, it has those asymptotes. So, and I'm like, no, here's pi. Okay, what is secant doing at pi? It's approaching 1. Y'all, slow down on the test. Okay. All right. Now, I've gone pretty quickly through um, the limits. There's certainly more kinds of limits, lots more details, lots more things to contemplate. Remember that there's, what did I say, 7 hours, I think, of limits in this series. So if you need a refresher on any of it, please go back and find those. And we're going to start on derivatives. I've spent a bit more time on limits that I'm going to spend on any individual other section within the typical Calculus 1 class, because limits has been the farthest back from where you are now at the end of the semester. Again, if you're using this for kind of a once over the top review for a final type occasion, um, I'm just going over the top really lightly. For instance, we're going to spend maybe 30 minutes on derivatives, and yet in this playlist, there's 21 videos with over 11 hours of everything you never knew you wanted to know about derivatives. So keep in mind that, this is just highlights, just kind of little tidbits. So let's start off with derivatives. Remember, you had the power rule, the quotient rule, the product rule, the chain rule, all sorts of neat things like that. I'm not going to be dealing with a lot of the transcendentals, like with the hyperbolics and inverse trig and so forth, because a lot of students don't have that in their Calc 1, but they are in those 11 hours worth of videos on derivatives alone. There's some standalone videos on all of those in there, so feel free to go back and look those up. So let's just stick to algebra and the basic trig, cosine, sine, and maybe a little bit of e to the whatever, ln x, but not getting into the ones that typically require vast memorization or even a formula sheet for the different variations. All right, so let's start off. And let's just start off with the chain rule, because it will incorporate all the other parts at some point or another. Now, in algebra class, way back when you first started learning algebra, they had you work from the inside out. Remember, you had parentheses, and you'd start with the innermost parentheses and work your way out, and then work your way out some more, and then work your way out again. Well, when you're doing the chain rule, you actually go backwards. You go from the outside to the inside to the inside, however many times you have to get to the inside of whatever else nested. All right. So it's crucial that you identify what the outside is. Now, sometimes to find what the outside is, it's easier to start from the inside, work your way out, and go, okay, so this is a cosine x squared. This is a secant cubed x squared. That's the inside of those parentheses. And then when you work your way all the way out, you have a product. So the outside of this, excuse me, is a product rule. So when you do the chain rule, you start from the outside and you work your way back in. All right. So the derivative, we would say, okay, the product rule, it's the first. Now this secant cubed x squared, sometimes it helps students to write it the way it actually is. It's the whole thing being cubed. It's the first times the derivative of the second. Excuse me. And the derivative of cosine is negative sine. Leave the inside alone. Loop back in and take the derivative of the inside. That loop back in is where they get the chain from. Okay, now this is just the first times the derivative of the second, plus the second, as is, times the derivative of the first. So we're going to treat it as this secant x squared cubed. I'm going to write it here so you can see it. Secant x squared cubed. So you bring the power down, leave the inside alone, take 1 off the power, loop back in and take the derivative of the inside. Well, the derivative of secant is secant tan, right? So we'd have secant of x squared tangent of x squared, loop back in and take the derivative of x squared, which is 2x. All right. Now, you can see that this cosine of x squared cancels that secant of x squared. So cleaning this up, we could factor out a secant squared of x squared and a 2x. And that would leave us, I guess we could do the little curly braces to make it a little bit more clear. Secant x squared minus sine of x squared plus 3 tangent x squared. All right. So we would have 2x, just cleaning it up a little bit, squared x squared. Excuse me. Times. All right. Now, minus sine times secant. Secant is 1 over cosine. So minus sine times 1 over cosine is minus tangent of x squared plus 3 tangent of x squared. So 3 minus 1 tangent x squared is 2 tangent x squared. So this would be 4x secant squared of x squared tangent x squared. Now, some of you may have noticed at the beginning and thought, well, hey, wait, won't this cosine cancel out one of those secants because that's 1 over cosine cubed, right? And that's actually true. I wanted to show you the long way. But you could have reduced it at the beginning and said one of these cancels out one of those. And so what I'm actually going to be trying to take the derivative of is secant x squared squared. So it's not the product rule at all. You would bring the power down, leave the inside alone, loop back in and take the derivative of the inside. So you would have secant x squared tangent x squared, loop back in again for 2x. And this immediately gives you 4x secant squared x squared tangent x squared, which is considerably faster, but the same answer. So keep in mind that, depending on your teacher, right, and just depending on how things fall, you should always take a second at the beginning to see if you can simplify a problem before you get started. So let's try another one. Let's try y is x squared plus 2x over 3x plus 4 cubed. Now, you have a fraction inside parentheses, and then it's cubed on the outside, so it's the power rule, because that's the outside is the power. So it's the power rule, and inside is the quotient rule. So here we go. We start with the outside. So the outside says bring the power down, leave the inside alone. Take 1 off the power. Now we're going to loop it back in. And on the inside, it's the quotient rule. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. If you don't have that clearly defined in your mind about you start with the denominator, right, when you're going the bottom times the derivative of the top, it's going to really impact all the problems that require the quotient rule. So please be careful. So here's 3. Here's my x squared plus 2x over 3x plus 4 squared times. And when I clean up this numerator, I would have 3x squared plus 8x plus 8 over 3x plus 4 squared. Now, then we can kind of combine these, and we would have our 3 times our x squared plus 2x squared 3x squared plus 8x plus 8 over 3x plus 4. But do you see how this 3x plus 4 down here is squared? Right there. It doesn't look like a square. Squared. Okay. And this square applies to here. So it's kind of a hard to find square. So this is to the fourth. Now, we could factor out an x from right here. And when we do that, because we're going to factor it out of here, so we have x squared plus 2x squared. So this is x times x plus 2 squared, right? So when we factor out this x, it actually is an x squared. So we would have 3x squared, x plus 2 squared, 3x squared plus 8x plus 8 over 3x plus 4 squared. Now, you might say, well, speaking of trying to clean things up at the beginning, couldn't I have taken the x out right here? And that would have had y be x times x plus 2 over 3x plus 4. And that's very true. You could do that. No problem at all. But I'm not going to do the problem. Okay. But what would happen is it would start off the same. You would bring the power down, leave the inside alone, take 1 off the power. But when you loop back in, now when you do the quotient rule, you have the product rule embedded in the quotient rule. Does it make sense? So you'd have the bottom times the derivative of the top. And the derivative of the top is not the derivative of x squared plus 2x. It's the derivative of a product. So it'd be the bottom times the, you'd have this bottom. And then you'd have the product rule. And then you'd have minus the top times the derivative of the bottom. I mean, it's so easy to get lost over here. So sometimes I hate to say it's if you're looking at it going, oh my gosh, this is going to make another layer. Okay, over here it's simple. Up here it simplified it, right? But here it would add another set of parentheses, right? And so that's just going to make us do more chaining. I'm not sure that would be your best bet. Okay. Now, one of the things that you'll use these for sometimes are position functions. So if you had given a position function, and let's say it's this, s of t is equal to 7t squared minus 8t plus 32, all right, where the position is measured in feet. And time is in seconds. Okay. If I take the derivative of a position function, that talks about how quickly you're changing your position. So think about it like going to work or going to school or going to the store. You would go from one position to another, and the speed at which you are changing positions is your velocity. So derivatives are rates of change, right? So we would take the derivative, and that'd be 14 minus 8 feet per second. All right. And then if I take the derivative again, I get 14 feet per second squared. Sometimes they spell it out. Some use SEC, some just use S. Now, because how quickly you change your velocity, right? Like leaving a stoplight and going through the velocity pretty quickly, that's your acceleration. If you want to find a specific position, right, at some time t, you would just substitute it in here and see where you are. If you want to find like a total distance as opposed to a position at any given time, then what you would have to do is to plot the velocity. And this velocity function if this is your velocity and this is your time, right? So this is 0 minus 8, and then it would have a slope of 14. So this is your velocity graph, and it's negative down here, and it's positive up here. So velocities are different than speeds. Velocities have direction. Okay, so once you set up and say, let's say to the right is positive, then when you head to the left, that would be negative. You could also say to the left was positive. So it just means the opposite of where positive is. So what you would have to do is find out when that changes, and using my calculator, this point right here is 0.57, or you could divide it out. 0. Okay, so from 0 to 0.57, you have a negative velocity. And at 0.57, it's 0. And from 0.57 to whatever the end time is that you're curious about, let's say it's 3 seconds in, you would have a positive velocity. So right in here, it changed directions. So you would have to find the position here, the position at the start, and this position at your end time. And then you would find this distance, and then you would find this distance, and then you would find the total distance by adding them together. Now, again, this is just really quickly over the top. Okay, so go back and find all the other videos if you want some more detail. Now, after you learned how to do the derivative with just y equals, which is explicit, because when you have s equals or v equals or a equals or y equals, like right here, this says explicitly what y is in terms of x. Implicit is where they're all kind of jumbled together, and it's an implied relationship, but it's not explicitly spelled out. That's the difference between the two. So if you have x's and y's mixed up, then you would do the implicit form, right? And so just as a quick reminder, you'd have your 2. X times y squared is a product rule, so you'd have the first times the derivative of the second. So you bring your power down, leave the inside alone. Since we don't explicitly know what y is, we would loop back in and take the derivative of it again in case it's self-differentiable. Okay, so this is 2 times the first times the derivative of the second plus the second times the derivative of the first. Now, if you go, well, why don't we do the same thing to x? You would take the derivative of x with respect to x, because dx over dx is 1. Okay? Minus 3, the first times the derivative of the second, plus the second times the derivative of the first. And again, if you loop back in on that x, it's going to be dx over dx. Derivative of 4 with respect to anything is 0, and this is 6. So you would have 4xy, you gather up your dy dx's, plus 2y squared minus 3x squared dy dx minus 6xy equals 6. So factoring out the dy dx's, you'd have 4xy minus 3x squared equals 6 plus 6xy minus 2y squared. Then you could divide through to get dy dx isolated. And you'd have 6 plus 6xy minus 2y squared over 4xy minus 3x squared. And you could factor a little bit. You could get a 2 out of the numerator. and an x out of the denominator if you want. And there's a whole video on implicit. All right, so if this just went by way too fast and you're like, oh, wait, I didn't quite get that. There's a whole video. All right, now we could talk about rate of change. If you had some sort of a function, and I group my stuff by topic rather than necessarily chapter. So a rate of change goes with your derivatives, all right? Except it sort of is a bridge point back to your algebra class. So if you had something like y is equal to x minus 1 squared plus 2, this is actually a parabola that got shifted to the right one and up 2, so it looks kind of like this. All right. Now you could, when you were in algebra class, right? I could ask you, to give you a couple of points. Okay, and I could say, well, let's talk about when x is 2 and when x is 5, right? So let's find where those points are. So if x is 2, y is 2 minus 1 squared plus 2. So y is 3. Okay, so this point, let's say, is 2, 3. And when x is 5, y is equal to 5 minus 1 squared plus 2. So y is equal to 4 squared is 16 plus 2 is 18. So this is 5, not drawn to scale, obviously, 5/18. All right. If you find the slope between these 2 points, as if there's a line there, okay, then that would be your average slope. So the average slope is your algebra slope. It's the difference in the y's over the difference in the x's. So this would be 15/3, which is 5. So an average slope is your algebraic slope. You would have to have 2 points, find the slope between those 2 points. An instantaneous slope, okay, so this is the average slope, right? The instantaneous slope would be the slope at a specific point, not between 2 points, but a slope at a specific point, and that's the derivative. So the instantaneous slope is the derivative evaluated at a point, okay? So let's say that we want to find the instantaneous slope at x is equal to 2. Then we would need our y value, but we already calculated that up. So from before, x is equal to 2, y is 5, right? And then y is x minus 1 squared plus 2. Now you could take the x minus 1 and square it out, but let's just take the derivative the way it is. So you bring the power down, leave the inside alone, take 1 off of the power, loop back in, and the derivative of x is 1. So this is and the derivative of 2 outside there is 0. So y prime is 2, and x is 2 for what we're curious about. You would substitute that in, 2 minus 1. So y prime turns out to be 2. Okay, so that's the instantaneous slope at this point right here. All right, so this would be the instantaneous slope. Once you know what the instantaneous slope is, you could actually find the equation of the tangent to the curve at that point, and you do a lot of that. So remember that the equation for a straight line is y minus y1 is m times x minus x1. So y minus, because remember we had x is 2, y is 5, right? So y minus 3. I'm sorry, I said 5. I don't think it is 5 up there. It's 3. I'm so sorry. Thank goodness we haven't needed it before now. Y'all are probably going, oh my gosh, I thought I knew what I was doing. No, it was me that had a moment of insanity there. All right, so y minus 3 is equal to the slope is 2 to x minus 2. So y is equal to 2x minus 1. Now that's the slope of the tangent. The slope of the tangent is 2, still there, right? And we could graph this pretty quickly using that slope y-intercept or mx plus b form. So this is the tangent. Sometimes they ask you about the normal to the curve. And if they want the normal is perpendicular to the tangent. Right. So if the tangent slope is 2, the normal slope is you flip it and you change the sign. But then you would use that same y minus y1. So substituting that in, you'd have y minus 3 is a negative 1/2 x minus 2. So y turns out to be negative 1/2 x plus 4. And this would be the normal. And if you plot these on your graphing calculator, they sometimes don't look perpendicular to each other because your window is not squared up. But there is a, if you're using like a TI, if you go up to the where you can set the table by hand or ask it to do it automatically, then you can have it square up and then it will look perpendicular. All right. So the next thing we would sometimes do is they have you do related rates with these. And related rates are where they describe a situation and they talk about one thing that's going on and then they ask you about how's that affecting something else. That's why they call it related. So as one thing's helping the other. Sometimes it's like, I don't know if you've ever done this, but if you take a balloon and blow it up and then you put it in a hot car, then as the temperature goes up, the the volume is related to the temperature change because the balloon will expand. Likewise, if you put it in the freezer, I don't know if you've ever done that or not, but it's kind of fun. Okay, if you put it in the freezer, as the temperature goes down, the volume is going to go down. So the volume is related to the temperature, right? Now, so we're going to talk about a typical thing like cars or motorcycles or people or airplanes. They're traveling in particular directions, and they talk to you about the path of the objects, the airplanes, the motorcycles, the people, and then they ask you not about the path velocity or anything, but how is that going to relate to the changing location, the change in speed? All right, as they get closer together or farther apart. So let's say you have somebody that's on a motorcycle and they're driving east to some location and they're driving, let's call that A, and they're driving at 50 miles per hour. And at this location right here, they are going to be able, they're going to meet somebody. Let's say that's B, who's also coming on a motorcycle and they're traveling a little bit faster. Maybe they're on a highway. Maybe they speed. Don't speed. All right. And they're going to meet at this location for lunch, let's say. All right. So they tell me about their paths. So this one's A's going east, B's going north. They're going to meet somewhere for lunch. This is their speeds. And then it says it wants you to talk about the speed between them. Let's talk about that as R, like from trig. Right. But they want to know what is going on there when B is 0.4 miles away, and A is 0.3 miles away. Okay, so that's the information that they give you. And so first, what you have to do on related rates, typically, is a picture helps immensely in many, many occasions. And you have to come up with a formula that describes the situation they describe to you, but also kind of is related to, well, I'm sorry, I didn't even mean to use related. It's related to the question they're asking you. So by Pythagorean's theorem, I can say that r squared is actually related to x squared and y squared if you consider this the x direction and this the y direction, from Pythagorean's theorem, right? X squared plus y squared equals c squared. I'm just calling it r squared. So then we're going to take the derivative. And when you're looking for a related rate and they're asking you how quickly, how fast, what's miles per hour, something like that, it's a time derivative. And none of these are in terms of time. So when you take a time derivative, everybody is implicit. Everybody gets looped back in. Up here, when we did implicit, we were taking the derivative with respect to x. So when we were looking at an x, it acted like normal. But now we're taking the time derivative with respect to t. Everybody is implicit. Okay? All right. I teach engineering, and the students say it isn't until dynamics class that they understand why they had to learn implicit differentiation. So you bring the power down, leave the inside alone, loop back in, and take the derivative of the inside, which is r. Bring the power down, leave the inside alone, take 1 off the power, loop back in, and take the derivative with respect to time. Bring the power down, leave the inside alone, loop back in, and take the derivative with respect to time. So the one that you're trying to find is this one. So everybody else has to be accounted for somehow in the information that they gave you. So you go 2. Okay, R is what I'm missing. I don't have any information about R. R is this distance between the two. So can you see anything in here that would let us be able to calculate up what that distance is at a particular time that they're curious about? Well, if this is 0.3 and this is 0.4, then this turns out to be 0.5. Your typical 3, 4, 5 triangle. So this would be 0.5. And dr dt, I don't know. That's the answer to the question of the day. So this is 2. X is 0.3 at that moment in time, traveling at 50 miles per hour. 2, 0.4 at that moment in time, traveling at 60 miles an hour. So when you solve all this, you get 78 miles per hour. Okay, let's do one more. And one of the examples that's kind of used very commonly is if you're blowing up a balloon. So let's say we have a large balloon and we're using a machine to pump it up, right? Because if it's so large, you can't blow it with your lungs. Okay, so we've got an air pump that's blowing this, and we have a large balloon. And the air pump is blowing it in at a rate of 0.4. I'm sorry. At a rate um, where the I'm sorry, where the radius is changing. At 0.4 inches per second, which doesn't seem like much, right? But the question is, how quickly is the volume changing? or increasing, which if you're blowing it up, when the radius is 40 inches. Okay, now you have to find some sort of equation, and so the volume of a sphere is 4/3 pi r cubed because a balloon is a sphere. So they're either asking you, how does one compare to the other, and it's changing with time, maybe saying how quickly, how fast. All right, so I'm going to take the derivative with respect to time, so that would be dv dt. This would be 4/3 pi because those are just numbers. You bring the 3 down, leave the r alone, take 1 off the power, loop back in, and take the time derivative. So what is it that I'm being asked to find? How quickly is the volume changing? So it's asking me for this one, which means everybody else has to be accounted for. So you have 4/3 pi times 3. And r is the radius, which at this moment in time is 40 inches. And then dr dt is 0.4 because that's how quickly the radius is changing. And so when you get this all cleaned up, it's 2560 pi cubic inches per second. Be careful with your units. That seems like quite a lot. Now the next thing we're going to do is remember how you took the derivatives and then you relearned everything you had forgotten about graphing from college algebra, where you learned about increasing, decreasing, maxes and mins. Then you also learned about critical numbers here in calculus. You learned about whether it's concave up or down. So we're going to do that next. For this brief review on the final review where we're hitting the highlights of the majority of topics for Calc 1, we're going to talk about integration. It should have been the last thing that you talked about in your course, so it should be the most familiar. I do have in this series 10 videos on antiderivatives and integration in areas for a total of 6 hours. Again, this is just supposed to be a kind of once over the top. This is everything that you did in Calc 1, or if you're wanting to know what's in Calc 1, this is sort of a once over the top. But there's, multiple, there's 52 videos on everything all together. So go back and look at the playlist if you have more questions. So when you learn to take all of these derivatives and then we're wanting to learn how to reverse it, you first are introduced to it as an antiderivative, which is anti or against derivatives going backwards. Then it's the indefinite integral, then the definite integral. So we're going to run through that really quickly. The only thing that you know at this point in Calc 1 is reversing the power rule, anything that you recognize by pattern, like the derivative of cosine is minus sine. So if you see a minus sign, its integral would be cosine. So, or things like inverse trig and hyperbolics. I'm not going to talk about inverse trig or hyperbolics. Those are in those 10 videos for the 6 hours. You can go look at them there. We're just going to briefly touch on antiderivatives and all that. So if I had y is equal to x squared plus 3x plus 6, I could ask you to find the antiderivative as if this was y prime, or I could write it as using this integral sign. And when you do that, this would be the power rule. So you add 1 to the power, divide by the new power, add 1 to the power, divide by the new power, and the integral of 6x is 6. And then since we do not have these values right here, which are the limits of integration, we can't evaluate it, so we have plus c. That's why it's called an indefinite. Okay, if you had values right here, it would be definite. The plus c is important. Remember, when you take the derivative of something, if it has a constant, the derivative of a constant is 0. So when you back it back up, you can't retrieve that constant without additional information. So this plus c is important. Teachers will take off for it. Computer programs will take off, or I take off 2 points every time it gets left off. All right. If you had something like, what's 2 secant x tangent x, this would be a pattern recognition, and you would say, what did I take the derivative of to get secant tan? That would have been secant. So this is 2 secant x plus c. That's this one. All right. Now, let's talk about doing a definite integral. So if you had, well, no, let's not do the definite integral yet. Let's do an indefinite one using use substitution. So let's talk about x cubed plus 3x plus 6 squared, 3x squared plus 3 dx. Now up here, let's look at this one. You had just a simple x squared, a simple 3x, and a simple 6. If you were going to take the derivative of this inside function, you would just use the power rule, right? Bring the power down, take 1 off the power. So you would not need to use the chain rule to take the derivative of this, right? If you had this part right here, see this power that's on the outside? That says you would have had to use the chain rule to take the derivative of that. You would bring the power down, leave the inside alone, take 1 off the power, loop back in, and take the derivative of the inside. So if taking the derivative of this would require you to use the chain rule, you're going to have to back it up using use substitution, right? So you get to choose what you want u to be. Look at the videos, it kind of talks about that. So u is x cubed plus 3x plus c. If I take the derivative with respect to x, so du is 3x squared plus 3 dx. I've seen some people solve this for dx and then and then change that over here. I'm not actually seeing any books like that myself, but I saw that the other day and I thought, now that's different. So if your teacher does the other way, you're going to have to rewrite these in your own mind. All right. So let's look. So du is 3x squared plus 3 dx. So this is du. It's equivalent to du. We said this was u. So this is u squared du. How do you integrate something like this when its derivative, remember, we had the dx right here, and that was the derivative of x, right? Differential. So this would be u cubed over 3, okay, plus c. Now, they didn't ask us about u, they asked us about x's, so we change it back, and we would have this 1/3, and u is actually x cubed plus 3x plus 6. We're going to cube it plus c. So it sort of reminds me of an algebra class when you did the change of variable technique. You have to remember to change it back. What if you had a variation of that? X cubed plus 3x plus 6 squared, and what you have over here is x squared plus 1. Now remember, we found out that du from before was 3x squared plus 3 dx. So this is what I want. I want 3x squared plus 3 dx, and all I have is x squared plus 3. But this can be factored out and says all I'm really missing is a 3, right? So I can insert a little multiplier by 3. And you go, well, how is that legal? If you undo it. Okay, so multiplying by 3 and dividing by 3 is the same thing. So you would have, I'm sorry, I think I just said multiplying by 3 and dividing by 3 is the same thing. Multiplying by 3 and dividing by 3 cancel each other. Sorry about that. Oh my goodness, that's terrible. All right, so now what you have is you have the integral of, this is u squared du again, because this is your du right here. Now, so this 1/3 is the one that we acquired, okay? When you integrate u squared du, you get u cubed over 3. This 3 is a result of the integration process. So you have 1/9 u cubed plus c. So this is 1/9 x cubed plus 3x plus 6 cubed plus c. All right. So let's do one that's now, let's do a definite integral now. So what if we had 0 to pi over 2 of cosine 3x dx? Now, if I was to take the derivative of cosine 3x, because cosine 3x is the derivative of something, we're trying to figure out what that something might have been. And if I took the derivative again, I would take the derivative of the outside, leave the inside alone, loop back in and take the derivative of 3x. So it would require the chain rule to take another derivative. So it requires substitution to back it up. So the inside that we would loop back into is 3x. So du dx is 3, du is 3 dx. So what I need, again, is a 3. And I had the dx because this is a picture of what I want. So I cancel out what I just did by multiplying by 1/3. So 1/3, 0 to pi over 2, cosine u du, because this is du. Now, these numbers right here are x values. So keep that in mind. So you'd have 1/3. What did you take the derivative of to get cosine? It would have been a sine. Now, again, these are x values. So you cannot substitute an x value into u. You would substitute u values into u. So I change it back. So like I said, the change of variable technique. And now I can insert an x value into an x. So I have 1/3 sine of 3 times pi over 2 minus sine of 3 times 0 equals 1/3 times minus 1 minus 0. So it's negative 1/3. Alrighty, let's do one more. 0 to 2 of dx over 5x plus 1 can be written as integral from 0 to 2 of 5x plus 1 to the minus 1. So u would be 5x plus 1. Du dx is 5. Du is 5 dx. So what I need is this 5 dx to make du. So I undo what I just did, cancel out what I just did by multiplying by a fifth. So I'd have 1/5, 0 to 2 of u to the minus 1 du. Now, this is one of those pattern recognition ones. What did you take the derivative of to get 1 over u? That would have been the natural log. So that would be the natural log of u from 0 to 2. Now I want to show you two ways to do this. Right? One way is to say, all right, I have 1/5 the natural log of u from 0 to 2. These are x values, so you cannot substitute them straight into u. So you have 1/5 the natural log. So change it back to x's. And now you can utilize the 0 and the 2. and you'd have the natural log of 5 times 2 plus 1 minus the natural log of 5 times 0 plus 1. So it's 1/5 the natural log of 11 minus the natural log of 1. And if you are subtracting logarithms with the same base, you can compress it into a single logarithm by dividing. So this is 1/5 the natural log of 11, or the natural log of 11 raised to the 1/5 power. Okay, now that's the way we've been doing it. You can actually change these x values for your limits of integration to u values. So let's try that. So you had 1/5 the natural log of u, and up to now we've been trying to keep track of the fact that we had x values, can't substitute into u. Now remember, we said u was 5x plus 1. So if x is 0, looking at this lower limit, we'd have u for that is 5 times 0 plus 1, so it'd be 1. And if x is 2, u would be 5 times 2 plus 1, u would be 11. So we would use these numbers and say this is 1/5 the natural log of u evaluated from 1 to 11. So you'd have 1/5 the natural log of 11 minus the natural log of 1, which is this same part. So you see how you end up in the same spot? It just is a matter of how you're wanting to get done with this, whether you want to keep it in terms of x or change it. Sometimes your teacher asks you to change it. Sometimes you end up with an extra variable, like maybe looking back up here, like maybe you'd have an x. And what do you do if you've got one that you don't particularly want? Okay, how do you get rid of an extra variable? And so if you go back and look at the videos that were the more complex ones, those 6 hours of videos, then there's some in there that are demonstrated for that. But for right now, we're just sticking with kind of once over the top lightly. So the next thing we're going to do is to talk about the last kind of little theoretical applications of this integration, where we talked about the average or mean value and where we talk about area. So let's get started on that. So let's find the average or mean value of an integral. But before we do, I just kind of want to quickly remind you what we've been up to. So in the video where I demonstrate Riemann sums, we talk about finding the area under a curve between A and B. And you find that area by integrating from A to B f of x dx. So this is an area. Now think of just a simple rectangle for me. The area for a rectangle is the base times the height. So if I take the area and I divide it by the base, I would get the height. So what they're doing with this average is they're saying you have some sort of a shape. And what I want to do is to find an average y value, an average height. So I'm going to divide this by the base and come up with the average height for a rectangle. So this would be the average or the mean value, which is a y value, right? So let's try going from 3 to 5 of 1 plus x squared x dx 5 minus 3. Now one thing you could do is to say u is 1 plus x squared du dx is 2x du is 2x dx, and modify this by using your u substitution, or don't forget your algebra. So you could integrate from 3 to 5. Same problem, 3 to 5, and just multiply this out. And you would have x plus x cubed dx, which to take the derivative of that would just require the power rule. So backing it up just requires the power rule. So you would have 1/2. Okay, and integrating from 3 to 5, you would have x squared over 2 plus x to the 4th over 4 from 3 to 5. And when you do all that, you get 72. If you work this one out the same way, you're going to get 72. So we've been working on doing these integrations. I think you can fill in these missing steps right there. And let's move on and talk about areas. Once they use the word area, finding the area, that should trigger you, and there's a whole video on this, that should trigger you to say, oh, I've got to plot it, right? Because what you have to do is to decide where it's above and below the x-axis, if that's one of the boundaries. Let's talk about that. So if you had finding the area bounded by y is equal to x cubed plus 3x squared minus 4x minus 12. So you want it bounded by that, the x-axis, which could be y is equal to 0 is another way to say the x-axis. X is equal to -4, and x is equal to 3. So they're wanting you to find the area bounded by all of that. So as soon as they say area, though, I'm thinking, I'm going to have to graph this. So let's talk about x cubed plus 3x squared minus 4x minus 12. There's an x squared in common. There's a 4 in common. So you'd have x squared minus 4 times x plus 3, x plus 2, x minus 2, x plus 3. So you've got a minus 3, a minus 2, and a 2. Now, this is cubic, so the end behavior is the same as a cube, and you did all this in your graphing section. So it starts down here. It's going to, the multiplicities are 1, so it's going to cut through. And you don't care about drawing it to scale, you just want to know what's above and below. So here's 4. We're going to go, to 3 on this side. And over here on this side, we're going to go to -4. So this area is negative. This area is negative. This area is positive. And this area is going to be positive. If you just go and integrate straight from -4 to 3 for this, then the positives and the negatives are going to cancel each other out, and you're going to effectively get a net sum. So we can't do that. So I know when I integrate this, I'm going to get a negative in this first section. So I need it to become positive. Some teachers will have you take the absolute value of it. Some just say, we'll put another negative in front, and that'll be the opposite of what you got. So that'll make it positive. So each one of these sections right here is going to result in a negative value. So I either need to have an absolute value sign or a negative sign in front of it that's going to take care of it. So this first one, from -4 to -3, is going to result in a negative number, so I'm putting a negative in front of it to make it become positive. From -3 to 2 is going to, according to my drawing, result in a positive number. from -2 to 2, -3, this should be a -2 down here. From -2 to 2 of x cubed plus 3x squared minus 4x minus 12. I'm going to get another negative value, so I need a negative to make it become positive. And from 2 to 3, I'm anticipating a positive version. All right, so then when I integrate this, I'm going to have the negative of x to the 4th over 4 plus x cubed minus 2x squared minus 12x from -4 to -3 plus, same thing, x to the 4th over 4 plus x cubed minus 2x squared minus 12x from -3 to -2, x to the 4th over 4 plus x cubed minus 2x squared minus 12x from -2 to 2, and x to the 4th over 4 plus x cubed minus 2x squared plus 2x. Have this memorized by the time you get done, from 2 to 3. And when you do the math and clean this up, you would have the negative of -4.75 plus 0.75 minus a -32 plus 13.25. So do you see how these two numbers that I expected to be negative were negative? So it was a good thing that I changed the sign or use absolute value bars. And when you add all this up, you get 50.75. Now, this is the end, the review like you might do before a final. Maybe you searched on this and accidentally found this kind of Calc 1 review. But if this was your course and you've got to the end of this, you should take just a second, maybe a full minute even, okay, and congratulate yourself on getting here. You may or may not have the grade that you absolutely want, but you made it, okay? You got here. You learned a lot. This is a difficult course, so be glad and be proud of yourself, okay, that you survived, that you got to this point, and you can breathe sort of sigh of relief. What you don't do is after you finish this course, you put it all aside, okay, and go, glad that's over. All right, because what's going to happen is the day you walk into Calc 2 class, they're going to expect you to be able to do this first thing. I know some Calc 2 teachers who slap a piece of paper down on the desk and say, let me see what you remember from Calc 1. So please do not forget these things. Don't do a mental erase, and good luck in Calc 2.